Have you ever typed a simple command into your computer, I mean anything, and just stopped and wondered, what is actually happening right now? How does that string of text make something happen? Well, that's exactly the journey we're going to take. We're going to peel back all the layers, starting from your keyboard and digging all the way down to the core logic that makes everything tick.
All right, so here's our roadmap. We're going to start on the surface with the commands that we all type. Then we'll dive deeper into the language the machine actually speaks. From there, we'll look at the simple rules of that language, see how it handles some surprisingly complex ideas, and then finally, we'll see how those abstract rules get built into physical circuits that actually do the work.
So, our journey starts at the most direct point of contact you can have with your computer, the command line interface, or the CLI. Forget all the fancy icons in Windows for a sec. This is where you get to talk directly to the operating system. No filter, no graphical fluff.
And what's kind of cool is that whether you're on a Mac using something called Bash or a Windows machine with PowerShell, the basic ideas are pretty much the same. The commands you use to list files, copy them, move them around, they all share the same DNA. It's like a common language for getting things done, no matter what system you're on.
So, think of these as your basic toolkit. You can make a new folder with mkdir or get rid of a file with rm. But the real magic, the real power, comes from this little symbol right here. The pipe. It lets you chain commands together. So say you've got a massive file and you want to find every line that has the word error in it. Well, you could use one command to find those lines and then pipe that result straight into another command that counts them up for you. It's just an incredibly elegant and powerful way to combine simple tools to do complex jobs. Now, if you ever run the lsl command to get a detailed file list, you've probably seen this cryptic-looking string of letters. It might look like gibberish, but it's not random at all. Think of it like a bouncer for your files. It breaks down permissions into 3 groups: the file's owner, the owner's group, and then just everybody else. And for each of those groups, it sets 3 simple rules. Can they read the file, can they write to it, and can they run it as a program?
Okay, so we've seen how we can give the computer instructions. But what language is the computer actually thinking in? Because it's definitely not English, and it's not really LS or CP either. There's something else going on under the hood.
Deep down, a computer's world is incredibly simple. They don't use the 10 digits that we do in our decimal system. Nope, they use binary. It's a base 2 system that only has 2 options, 0 and 1. You can think of it as off and on, or false and true. This is it. This is the native tongue of all digital logic.
So, to make this real, let's take a number that we recognize instantly, like 88. How does a computer, which only gets zeros and ones, see that number? It has to have some way to translate it, right?
The process is kind of like making change. You start with 88, and you find the biggest power of 2 that can fit inside it. In this case, that's 64. So you grab that, subtract it, and then you do the exact same thing with what's left over, which is 24. You just keep doing that until you've got a perfect combination of these powers of 2 that adds up to your original number.
And this is what you get. Each spot in this 8-bit number represents a power of 2. The ones are basically flags, showing us which powers we needed to use, a 64, a 16, and an 8. So to a computer, this sequence of on and off switches, 0, 1, 0, 1, 1, 0, 0, 0, that is the number 88. Okay, so we've got our language of zeros and ones. But, language is pretty useless if you don't have any grammar, a set of rules for combining words to actually make sense. For binary, that grammar has a name, Boolean Algebra.
Now, this table might look a little intense at first, but the ideas behind it are actually super simple. These are just the basic rules for how ones and zeros interact using operations like and, or. For instance, look at the annulment law. It just says that any value ANDed with a 0 is always 0. Which, yeah, that makes sense, right? These simple rules are the absolute bedrock of every single calculation a computer ever makes. And among all these rules, De Morgan's theorem is a real superstar. It shows this really cool, really clever relationship between and or. What it means is that you can turn an and operation into an or operation just by flipping all the inputs and the output. This is a game-changing trick for engineers trying to design the simplest and most efficient computer circuits possible. So we can represent numbers, and we have rules to play with them. But how does a system that only has zeros and ones deal with something a little more abstract, like a negative number?
Yeah, this is the really critical point. There is no minus sign in binary. The computer can't just stick a little minus symbol in front of a number. It needs a system, A really clever method to show that a number is negative using only the ones and zeros it has to work with.
And that solution is a beautifully simple trick called 2's complement. It's just a 3-step process. First, you take the binary for the positive number. Second, you just flip every single bit. All the zeros become ones, all the ones become zeros. And for the last step, you just add 1 to that new number.
And that's it. That's the result. So when a computer is told to treat this number as a signed value, that leading 1 acts like a secret signal. It tells the computer, hey, what you're looking at is a negative number. And the machine knows to use the 2's complement rule to figure out its value is negative 22.
But, this system isn't infinite. A computer only has a certain number of bits to work with for any given number. So, if you do a calculation and the answer is just too big to fit in those available slots, you get an error called an overflow. It's literally like trying to pour a gallon of water into a pint glass. The extra just has nowhere to go.
We've covered the commands, the language, and the rules. So for this last section, let's bring it all home. Let's see how all of this abstract logic becomes real, physical circuits that are etched right into a piece of silicon.
Okay, so this is a logic circuit diagram. It might look like a crazy schematic, but each of those symbols represents something called a logic gate. It's basically a tiny physical switch that puts one of those Boolean rules, like and or, into action. It looks complex, but we can actually trace the flow of information through it, step by step.
All right, let's follow the inputs, A, B, and C, as they go on their little journey. See how the first AND gate combines A and B? At the same time, that NOT gate is flipping C. The results from those gates then become the inputs for the next set of gates, creating this kind of chain reaction. Each gate does its one simple job, and by stringing them together like this, we build up more and more complex logic until we get one single final answer at the output, Y.
And now for what is, to me, the most mind-blowing part of all this. We've talked about all these different gates, and, or, not. But it turns out you can build all of them, and therefore any computer that has ever existed, using just one single type of gate, the NAND gate. This is a huge deal for manufacturing, because it means you only have to figure out how to make one perfect, tiny, universal building block.
And that brings us right back to where we started. We began with a simple command, ls, and we followed that request all the way down to the electrical pulses firing through individual logic gates. That one simple keystroke kicks off this incredible cascade through all the layers we talked about, from text to binary, from binary to Boolean logic, and from that logic to physical circuits, and it all happens in a fraction of a second. It really is an amazing journey, and it's hidden behind every single thing you do on a computer.